Good morning, everybody. Thank you for attending our 78th Pioneers of Endocrinology Workshop. So this workshop started 17 years ago. Actually 18 because 1 year was COVID. We didn't have it. So 18 years we have been continuously running this. And this program has been a major showcase. And the reason behind that we built a very interactive program here where we collaborate clinicians from the med school as well as the basic scientists from the basic science department. So there are about 50 people, 50 members are in this endocrine program. They're all from all different parts of our school. As you know, we have 7 campuses, so 3 or 4 of them are part of these. Also, we have Seton Hall, local university, and they also participate with these. So this has been a really interactive program. And we also build from this program, we build a graduate program where we have endocrine research going on in basic science, as well as endocrine research in medical, clinical area. So that also has been worked out quite good. We have quite a few students now. Then we had a training grant, building all this interaction, and it has really helped us. But with this, we built this 18 years ago. But from these, we have the now Brain Health Institute, we have now alcohol program. So there are lots of institutes developed from this program. So I'm very happy that we are still maintaining it. So I'm also very excited to have our program today. If you looked at your booklet, you will see we built a very nice program. We brought pioneers of endocrinologists to speak in front of us. So you will have a good time here. We also have quite a few poster sessions. So the session will be pioneer speaker presenting for approximately 45 minutes. And then we'll have a lunch, then we'll have a poster session. But so I wanted to introduce here by bringing our research deans. We have 2 research deans are going to be attending, are already are here. They're going to be giving a short speech to introduce our program. First, I wanted to request Dr. Josh Kohut. He's the Dean of Research from School of Environmental SEBS. So, and followed by Dr. Murtha, Dean of Endocrine, Robert Wood Johnson Medical School. So first, Dr. Kohut, please take the podium.
Thank you very much. I don't know if you can hear me. I'm usually not good to be near microphones. Really appreciate the opportunity to come and speak with you all day. My name is Josh Kohut. I took on this role in January, so it's a new role for me. I'm a marine scientist. So I admit I had to ask my daughter last night to tell me more about endocrine science. And the reason for that is because I just understand the importance of the research. I understand the community that it takes to study this. And I thank Dr. Sarkar and this entire community for the effort that you have undertaken for the last 17 years to bring this community together. When I took on this role, I had a couple goals. One of the goals was to see how we could bring larger communities of scientists together to study research questions that have societal relevance, right? This is all of our goals, right? But there are ways in this role that I hope I can help our faculty maybe find connections that they weren't able to do in the past. This community has been doing it for almost 20 years, right? It serves as a great example of how we can bring different disciplines, different sectors, right? There's not just academic researchers here. You mentioned clinicians, but there's also private sector reps that are here, and most importantly, our students that are here, right? So I just applaud this community for taking on that really important challenge. It's not easy to collaborate across disciplines, across parts of institutions, and I just applaud you all for making that effort, taking that time to be here and sharing the incredible science that's enabled by this community. I want to welcome you here to campus. If there's anything that I can do in this role to support this group going forward, in addition to these workshops, because all the work happens between the workshops, I'm here to help. And so thank you all, and welcome to Rutgers.
Next is our Dr. Amy Murtha, Dean of Robert Wood Johnson Medical School.
Thank you, Dr. Sarkar. And what an honor and a privilege to be with you this morning. Again, my name is Amy Murtha. I'm the Dean of the Rutgers Robert Wood Johnson Medical School and the founding dean of what will be the new Rutgers School of Medicine. So first express my gratitude to Dr. Amorosa and Dr. Sarkar for their work, 17 years worth of work to keep this really important symposium and collaborative effort going. So thank you so much for all that you do. I'm an OBGYN by training, I should say first, so endocrinology of the bone is important to me too. I am a maternal fetal medicine specialist, so most of my work is really focused in pregnancy, but obviously this is a really important topic. I also want to thank Dr. Duque and Dr. Rosen for being with us today. What an honor and a privilege to have you here on campus. And just to share briefly, so the Robert Wood Johnson Medical School is on this incredible trajectory, a very exciting moment in our history. We're about to, in less than a year, open a new building. And opening a new building for a medical school is a moment. It's not something that happens. And this is especially important for us and exciting for us because we will be embedded now. Our first and second year medical students are moving out of Piscataway to New Brunswick, embedded in a new facility called the Helix in our Rutgers Health building. That Helix is a building that will be both full of innovation and technology. So the New Jersey Innovation Hub is 3 floors, med school is 4, and then Rutgers Health has 3 floors of clinical translational wet and dry lab space, as well as a vivarium on the top of the building. That building is spectacular. We'll have the latest in technology, and we'll embed the medical school and our students in a space where we can do what you all are planning to do today, is to collaborate, to come together as a community, to look for opportunities to partner in advancing science, advancing education. So really exciting moment for us. Right next to us, actually, the Nokia Bell Lab entire international research footprint is moving into the building next to us. It's actually starting to rise up from the ground as well. What an important moment for us as a medical school to be moving into a new space like that. And that comes at the same time that we're bringing 2 medical schools together. Again, in the spirit of the things that you guys are doing here today, bringing communities of like-minded, values-driven individuals that have the similar goals and objectives, and learning how to partner and collaborate to advance science, to advance education, to advance clinical care. Our medical schools, the Robert Wood Johnson Medical School and the New Jersey Medical School, are coming together to become the Rutgers School of Medicine. A moment in our history, again, that we will leverage to expand and elevate the work that's happening in every one of our spaces, including research, and to have us be partnering across the communities that are in this space is really important to us. There is so much added value by coming together, and Rutgers, having been at Duke and UCSF and coming here, I really deeply appreciate the depth and breadth of things that are happening in this university that we need to continue to leverage and work together on. So I don't want to take up too much of your time in the program this morning. I really just wanted to be able to come and say thank you all for being here. Thank you for organizing this event. I'm excited for what you all will do today and delighted to be here. So thank you.
I invite Dr. Lou Amorosa from Rutgers Medical School.
Well, good morning, everybody. First, I want to acknowledge and thank the colleagues on the committee who organized bringing two world-class scholars, both mineral metabolism scholars, to this symposium. I want to thank the deans for their very nice remarks. Well, I have the distinct pleasure of introducing Dr. Gustavo Duque coming. He is a world-class investigator on 3 continents. He began his medical career in Colombia, went to McGill to complete his clinical work in medicine and geriatrics, and his Ph.D. in basic bone biology. He stayed on the faculty at McGill for a while, and then the next thing we know is he's associate professor and chief of the division of geriatrics and head of a bone and muscle institute in Sydney, Australia for a few years. And from that position, the next thing we know is he's professor and chairman of the Department of Medicine at the University of Melbourne and the Australian Bone and Muscle Institute, with studying bone biology. So after about 7 years in that position, he had the credentials to come back to McGill as chairman of geriatrics, and again, head of another bone and muscle institute. In addition, with all this, he's the editor-in-chief of the Journal of Geriatrology, Biological Sciences. I don't know how people do this. And he wrote about over 300 articles, both articles, basic articles, and in chapters. And so I'm just privileged to have you join us today to teach us a little bit about your observations in the crosstalk with aging between muscles and bone. So thank you for being with us.
Good morning, everyone. Thank you very much, Louis, for the nice introduction. And thanks to the organizing committee for inviting me today. I must admit I feel very much a pressure because I don't consider myself a pioneer. And it's my honor to be sharing the podium with 2 real pioneers, with Sue and with Cliff. As I say, there's a big responsibility what I have at this moment to fulfill those shoes. So I will just start with a survey, a poll here. Could you please raise your hands if you have heard about the term osteosarcopenia? Oh wow, that's more than I have seen in many other audiences. Now, could you please raise your hand if you have heard the concept of geroscience? Okay, so now it's about 4%. The other one was about 30% or 40%. So that's part of what I'm going to talk today. So I will start with my conflicts of interests. Let's start. And when I received the invitation, and I know this was going to be a workshop on bone, but I mentioned that I work on both muscle and bone, and that I was going to provide some of information on how we understand that interaction now. How we understood that interaction in the past, and what I was told when I was a medical student and a resident in internal medicine, and even when I was doing my PhD in bone, was that muscle and bone are connected via mechanical forces. And that bone biology and bone metabolism was very much regulated by the connection between the muscle and bone. This is a very small pointer, but I will try to show it that way. But then the field started moving forward, and I would like to highlight this important paper by Marco Brotto and in the Bone World, who reported a new understanding of how bone and muscle were connected in a way that there is still a mechanical communication, but they highlighted the importance of the biochemical communication where multiple factors are secreted by bone that could affect muscle biology or vice versa. So when we talk about communication between two tissues, we have to think about how do they send the message. And because a lot of the people in the audience are endocrinologists or do research on endocrinologists, you know much better than I do and understand much better than I do all these different connections between tissues. You know that we work with hormones and we work also with cytokines, any of these factors that are secreted in a paracrine, endocrine, all these different kind of crines versions, and then they communicate, they send a message. If that factor is solved in the serum, whatever tissue that has receptors will respond in some kind of biological response. But the communication between tissues has also changed. Our understanding of how do they communicate has also changed. Now we know that they can package a message and they can send that cargo and send the cargo from one tissue to the other through specific packages that we call exosomes and extracellular vesicles, which are again packed in a way that they have a specific message. So it's not that general message that a gland releases when they release the hormone. It's a specific message that one organ can send and whatever the other organ wants to do. However, these messages can be good or they can also have a deleterious effect on the target organ. So what I'm going to summarize today is the new evidence of how we understand the response from both tissues, muscle and bone, to these kind of messages. Not only the cytokines, but also the hormones and the new era of exosomes and extracellular vesicles. But let's start with those factors that we know very well the muscle produces or the bone produces that could have an impact in the other organ and vice versa. Of course, I'm not going to go over all of them, these numbers, and I will show you later on how these factors, the number of factors is going, it's growing exponentially as we speak. But what we know is that there are some of these factors, and I'm sure some of you have been working on these factors for a while, they can have an impact on the other organ. And I will bring you examples, a summary that we did, we published a while ago, just to give you a couple of examples. I'm not going to go into the whole, interaction on biology or effect in specific cells, but I can give you two examples. One, and this is the case of osteokines, which means cytokines that are secreted by the bone, which go to the muscle. And the typical one is the osteocalcin. So osteocalcin is secreted by osteoblasts, and we know that when this osteocalcin works, is secreted from the osteoblasts, increases insulin sensitivity, and interestingly, as there is enough evidence in animal models that it increases glucose uptake in muscle and muscle strength. And again, this was reported in 2020, and I'll show you the update that we did, because we know that, for instance, if somebody exercises, the amount of osteocalcin that is produced increases. And that osteocalcin that is secreted reaches the muscle and has this biological effect in muscle. Does it have a biological effect in other organs? Yes. But the most significant effect that we observe is in muscle. And then we have the opposite, a relatively bad osteokine, sclerostin. And in sclerostin, we know that it's secreted by osteocytes and inhibits osteoblast formation. But what we know now is that sclerostin also has a negative effect, a negative impact on muscle biology. So let's assume, and I will mention that later on as well, that somebody, instead of exercising and taking, and increasing their levels of osteocalcin, instead of that, they remain in bed. They are admitted into the hospital, for instance, and they remain in bed for a specific number of days. They will start producing this sclerostin in levels that will not only affect osteoblast formation and bone formation, but also affect muscle formation and muscle metabolism. Now, the other side of the story. Again, I'm bringing some examples and I will just take you back and forth from my basic sciences and clinical sciences. But in the case of myokines, those cytokines that are secreted by the muscles and then reach the bone, I will bring you two examples as well. One of them is a negative one, myostatin. This is probably one of the most better known proteins secreted by the muscle, but in the muscle. And interestingly, this myostatin has an effect, an inhibitory effect on muscle growth. Yeah. So again, we have the example of somebody who is in bed rest. They are going to produce more myostatin. Therefore, they are going to have less, lose muscle. But interestingly, it also affects bone because it induces osteoclast formation. So there is more bone resorption, and we lose bone at the same time that we lose muscle. And if we look at the positive factors, I know there are people here who have been working on IGF-1 that is secreted by the muscle in conditions that are physical activity, and same with the interleukin-6 that is secreted by the muscle in conditions of physical activity. Two examples of positive effect. But you tell me, okay, this evidence is from mice. Well, we are moving forward into understanding the role of these cytokines in humans. And how do we do that? We have done that. We and others have looked at cross-sectional correlations. So people say, cross-sectional correlations, but it's the starting point to understand what the effect of these cytokines may have on bone, on these tissues. So for instance, this is a study by Itamar Levinger from Melbourne that we published in 2014, a while ago, where we reported that under-carboxylated osteocalcin, remember, an osteokine secreted by the bones, correlated with the strength measures in older women. So it was not a lot of participants, 90 participants, but the mean age was 75. So this was a real correlation between the levels of osteocalcin coming from the bone. There is no other tissue that would produce that. I mean, there are other tissues that produce very small amounts, but the main source is the bone. With the sclerostin, there have been this growing evidence that there is a correlation. This is a Korean study in 240 Korean women, also 75 and older, who mean age, sorry, that have low muscle mass and high sclerostin levels. So the ones with the lowest level of sclerostin had the worst performance. Independently, all this is adjusted for the level of physical activity or other potential confounders. I know, I don't think I have to explain here in this audience what the rank ligand is, but just to give an idea, we know that rank ligand is a member of the tumor necrosis factor cytokine family, which is secreted by several cells, mostly osteocytes in the bone, and this rank ligand basically stimulates osteoclast activity and bone resorption. That's well known. What we didn't know until very recently is that rank ligand also has an effect. Rank ligand activation has also an effect on muscle. That high levels of rank ligand activation has a pro-inflammatory effect, has an effect on muscle in a way that it initiates protein breakdown and also induces muscle atrophy and weakness. We didn't know that. So this is another way of looking on the clinical perspective, and that was done. That's the perspective from the basic sciences, and we say, okay, so let's do it. Let's test it in humans and see if this is the case in humans. If they have more rank ligand, then they have more poor muscle function, or they have muscle loss, or whatever. However, the main challenge for those of you who work with rank ligand is that the kits that are available, commercially available to measure rank ligand, are not very accurate, are very variable, sensitivity and specificity. So it's very challenging to measure rank ligand. So we have this challenge with my team, and we say, okay, how can then we measure rank ligand and demonstrate that activation on rank ligand is affecting muscle? So we, instead of measuring rank ligand, we measure another biomarker, CTX, C-telopeptide, which is a better, it's a surrogate that will tell us it's a surrogate of bone resorption, so it's a biomarker for bone resorption. If there is a lot of bone resorption, then we have more C-telopeptide. So instead of measuring rank ligand, because we don't think it would be more accurate, these tests are very accurate. They are used everywhere. They are well validated. They are used in clinical settings. So we correlated the serum levels of rank ligand, C-telopeptide, and we correlated with muscle function after many adjustments. And we found that these patients with higher level of rank ligand, this is in our Falls and Fractures Clinic in Melbourne, where the mean age of those patients is 82, and this one was 79 for this particular study. So we're talking about, as a geriatrician, I always refer to people older than 75. I rarely refer to people younger than 75. So for us, 65, 70 are babies. So we adjust for that, and we found that people with high levels of CTX, so high levels of bone resorption, have poor muscle performance. And we use SPPB with the short physical performance battery, which is a test that we use a lot in geriatrics to look at balance, muscle strength, and mobility. So this is just to give you an idea of how we have worked in terms of demonstrating this connection between the muscle and bone from the very biological different factors that are secreted by the muscle and the bone that may have an impact or have an impact on this. But the question is, how can we explain this to happen? What explanation can we find? So I will share with you the explanation that a geriatrician and aging biologist may have to all this situation. So I apologize if there are endocrinologists or specialized, because I give you the perspective of a geriatrician. So how somebody who works in aging will understand these changes in bone and muscle that happen with aging. Okay? So the first concept I would like to introduce is the concept of geroscience. This concept was developed at the NIA, at the National Institute of Aging, in 2014, and was then explained in 2014 by Brian Kennedy, who is a leader in this field, which I think is very interesting, because we, in aging and older persons, we see all these different conditions. You can see the list here of all the conditions that are observed and very highly prevalent in older persons. As clinicians, including myself, we treat disease by disease. So if somebody comes with hypertension, we give them the antihypertensive, we give them the diabetes, and then we treat the osteoporosis with the usual drugs and whatever. So in 2014, the people at the NIA say, we have been studying during many years these biological changes, biological mechanisms of disease that are triggered by aging. So what about, instead of treating disease by disease, we don't target the disease. We target the shared biological mechanisms. One or two of these mechanisms. And at the same time, if we target the mechanisms, we will be able to treat or prevent not one or two, maybe several of these chronic diseases. That's the geroscience concept. I hope I explained it clearly, but that's the way I understand it and how we understand it now. So when you look closely at these mechanisms, it has evolved into what we now know as the hallmarks of aging. And this concept is essential from how we understand this pathophysiology, specifically in osteosarcopenia that I'm going to mention today, or any other age-related conditions. So again, this was presented by Dr. Lopez Otin, who is a specialist in this and very well respected from Spain. We collaborate with Carlos a lot. And basically, you see here 12. They grew from 9 in 2013 to 12. And now some other people are, proposing 14 and 16. I still stick with the 12 that Carlos has proposed for a reason. is because these are really regulators and determinants of how a cell, a single cell, ages. And you can have, for instance, normal mitochondrial function, to give you an example, and the mitochondrial function could go down a little bit with aging, with normal aging, and go much lower or be much more affected in age-related conditions. And my team, and my lab, and my clinical team, we have 12 teams, each one dedicated to each one of these hallmarks of aging. And what we do is we work on the perspective of muscle and bone, aging and fat generation, but looking from one or several of these different. So what I'm going to show you today, what we have done, is a summary, very short summary, of what we do from our 12 teams of different people working from the very basic sciences into human studies and clinical trials. So this is our way of understanding it. So if you treat people with cardiometabolic disease and you look at the hallmarks of aging that are affected by those cardiometabolic diseases, you will see that you can explain them by looking at the hallmarks of aging. I invite you to have a look at what hallmarks of aging are affected in your disease of interest, and you will be surprised that at the end, a lot of them converge. So what happens, how we understand aging? And I was a little bit offended when a few colleagues of mine have told me, you know, you shouldn't be looking at the osteoporosis and sarcopenia because this is normal aging. And I say, well, I don't think this is normal aging. Osteoporosis and sarcopenia are well-known conditions and are accepted by the ICD-10 or 11 or whatever numbers now. So, you know, this is not, so basically people who think that way probably don't understand what the difference is between normal aging and disease. This is normal aging. This is a study that we did in Australia, the Australian body composition study with 15 participants from 18 to 88 years old. We used DEXA data from lean mass and measure in men and women. And basically what we did is elaborate or develop the reference range for lean mass in normally aging individuals. These were healthy, you know, they can have comorbidities, but the comorbidities are under control, so we consider them healthy individuals. I mean, that's one of the principles also that we do in geriatrics research, is we don't necessarily ask for somebody to be free of disease. I mean, it's impossible. It's impossible at this moment that somebody is free of disease. So this in healthy volunteers, and you compare the muscle curves in men and women with data from another study from Australia, the genome osteoporosis study, specifically in women, and then femoral neck and total hip. You see that the curves are relatively similar. And this is because, and I don't use the data on vertebral BMD because there is a significant change during menopause. But we compare with the femoral neck and the bone and muscle aging, you see that the curves are relatively similar. This is normal aging. This is normal aging. However, if somebody has or loses more than 2 standard deviation, so goes out of that reference range, or somebody, as we accept in bone, goes below minus 2.5, which is a little bit of, then those people are considered as, if they go below the standard deviation, we can consider them as having sarcopenia with other components that I'm going to mention soon, and then we have the bone, the osteoporotic patients. But I would like to highlight something that I'm sure Cliff is going to mention later on. I'm not going to give a lot of information on that, is that at the same time that we observe this decline in muscle and bone with aging, we also observe this increase in bone marrow adiposity and the amount of marrow fat. But interestingly, we also observe an increased level of muscle fat, and not this being totally independent of the BMI, totally independent of the diet, adjusted for many variables. We always observe that in aging bone there is an fat accumulation, and that we also observe in muscle. And this is this is from the UK Biobank with 9,000 people, 45 to 80. But this is not just one of many of studies that have been published in that point. So when they asked me to write this review for the Nature reviews in endocrinology, I told my team, okay, let's have a look at what the state of the art is now. And then we found a very complicated story. I hope you remember the previous one, you know, the simple one with a small group of cytokines one side and the other. Because now when we look at that interactions, those interactions, we see that there are now changes in the cargo, in the extracellular vesicles that have been identified. And you see here some in red, some in yellow. The ones in red are the bad changes. The ones in yellow are good. But going very quickly, we know that now it's not only based on 1 or 2 or 3 cytokines. It's a very complicated crosstalk system. But all this is triggered. All these changes are triggered by the hallmarks, by changes in the hallmarks of aging in a different way, different mechanism. But this is what we observe. And when we look at the other side of the story now, from muscle to bone, an effect of aging, we know that there are an accumulation of good things, but also accumulation of bad factors. Again, I'm not going to go into all of them because of the time, but something that we are working also a lot at this moment is the role of extracellular vesicles and how they change with aging and disease. And why is that important at this moment? We think not only because there are microRNAs. Usually, extracellular vesicles and exosomes one part of the cargo is composed of microRNAs. But interestingly, they can also carry many other things. We have seen, and when we analyze extracellular vesicles, we have seen microRNAs extracellular vesicles that carry not only microRNAs but also osteocalcin. We have found extracellular vesicles that carry rank. So, you know, this is interesting because they can have they can carry many of those components that could be good or bad to the muscle and bone at the same time. So that was another section that I wanted to take you through the way we understand as a aging biologist, we understand changes in muscle and bone from the normal aging to the pathological manifestations of osteoporosis and sarcopenia. So then comes to osteosarcopenia. I was really glad that most of the audience have heard about osteosarcopenia because we define osteosarcopenia as a syndrome that involves 2 well-known conditions. I must admit that I did my Ph.D. in bone, and I have even published books on bone, on osteoporosis. This is a summary that we published in 2022 by one of my postdocs. So we probably, somehow helped a little bit to understand bone. So for me, during my PhD and probably 2 years later, bone was the center of the universe. I was working on bone, passionate about bone. Sorry, nothing personal, Cliff. but I was passionate about it, and then I realized something, or we realized something. That fractured and osteoporotic patients, particularly the older ones, also have sarcopenia. And how we define sarcopenia, without going into all this, is that we have a decline in muscle mass, we have a decline in muscle strength, and we have alterations in muscle-specific strength. That's how we are defining now sarcopenia. Taking into consideration that the outcomes will be, in sarcopenia, impaired physical performance, mobility limitations, falls, fractures, inability to perform instrumental activities of daily living, poor quality of life, and mortality. So we have here 2 different conditions that affect muscle and bone, one that affects bone, the other one that affects muscle. But then we say, if the fractures are happening in people who suffer a fall or are sarcopenic, then there must be a connection, and that's why we and others propose that it should be understood as osteosarcopenia. So I will not go into this half of the slide and the mid part of the slide, because that's something that summarizes what I already said. But interestingly, we found, and many studies that we have conducted and others, looking at risk factors, and we found that they are exactly the same risk factors for osteoporosis and sarcopenia. We didn't find any different risk factor, any so far. Even we tried with genetic analysis, and we found that there are definitely some modulators of these changes in both muscle and bone. There are independent ones in muscle and independent for bone, but the ones that have osteosarcopenia have very much shared those risk factors. So people ask me, how are you going to define osteosarcopenia? We don't go into, we don't need a consensus conference or anything. I don't know, you know what I think of consensus conferences, especially consensus, because it's usually a group of experts who know each other. They are very good friends. They get together, they puff cigars, expensive cigars, they drink expensive cognac, and then they come with the same conclusions they had, you know, when they entered the room. So that's why I don't think we need a consensus conference to say that when somebody has osteopenia, osteoporosis as we understand it now, and at the same time has sarcopenia as we understand it now, we still need a definition for sarcopenia. We are working on it. That patient should be labeled as having osteosarcopenia. And osteosarcopenia is not necessarily exclusive of the normal aging and the worse aging and the presence of those risk factors. Osteosarcopenia could be also something that could happen acutely. And this is a summary of the evidence we have now, that if somebody spends time in bed, you know, when we admit these older persons into the hospital, they will lose 2 to 4.5% of their muscle mass each day of bed rest. And they will lose 1% in bone density in the vertebral column after 1 week of immobility, and up to 3.8% loss in the hip after 12 weeks. This is a summary of evidence. There are variability in between, but we have to keep it, the message is just to keep in mind that osteosarcopenia could occur very acutely in patients who are admitted into the hospital. What is interesting is that when we did and evaluated with some bed rest studies and some sponsored funded by the Canadian Space Agency, because, you know, we want to go to Mars, so we don't want our astronauts to develop osteosarcopenia during the trip. So basically, when we look at the biological changes that happen in this acute bed rest, is also similar to what we observe in the chronic age-related condition, or triggering the hallmarks of aging. So the way a geriatrician understands now osteosarcopenia is that vicious cycle where we have, the patient who is robust individual, which suddenly, because of the presence of risk factors, start triggering the hallmarks, and then changing in bone and muscle mass, then develops osteosarcopenia, present with falls and fractures, and then has the typical consequences of the osteosarcopenia, including frailty, disability, and institutionalization, and of course death. And now we understand this in a very much more complex way. We published this paper a year ago, where we try to look at the shared risk factors, the biological explanation, and finally the clinical consequences of having osteosarcopenia. Some people came back to me and say, unless you show that there are specific outcomes for osteosarcopenia, that doesn't exist. Maybe we see the outcomes of sarcopenia and the outcomes of osteoporosis, and when you combine them, well, you expect to have falls and fractures, of course. Well, to answer that question, we and others have worked a lot with many international cohorts. Basically, what we have proven so far, the ones here in red are papers from our teams in collaboration with other teams. Basically, we know that having osteosarcopenia increases the risk as compared to having osteoporosis or sarcopenia alone, or not having any of them. Okay? Having osteosarcopenia increases the risk of falls, of fractures, of frailty, of mortality, of depression, and limitation in activities of daily living. Now we also know, and that had to add the other line, is also much lower, much higher impact on quality of life. So you ask me if I can choose, what do you want to have, sarcopenia, osteoporosis, or osteosarcopenia? I would say probably I wouldn't go with osteosarcopenia. So that's where we are. We know that having osteosarcopenia significantly increases the risk of these adverse outcomes. So the message that we always send is, if we are going to treat osteoporosis, please think about the osteosarcopenia. That will be my last message today. So moving forward, and I'm almost done because I want to have give some time to for discussion. But I think we're doing well of time because I really want to share a lot of this with you today. Is that when we look at the pathophysiology, we found very similar changes. All of them, or most of them, associated with changes in hallmarks of aging. So we also observe, unstable genome, which is epigenetic alterations here, reduction of satellite cells, which is equivalent to a stem cell exhaustion, that we also observe in the osteoporotic bone. We observe apoptosis in muscle, which we also observe in bone. We observe alterations in autophagy in muscle, in sarcopenic muscle, which we also observe in osteoporotic bone. So this allowed us to propose, not long ago, that this is where we are now in understanding osteosarcopenia, again, from the aging biology, aging perspective. So we have risk factors which trigger and affect one or several of these hallmarks of aging. The person develops osteosarcopenia, and here are the outcomes. This is where we are. This is how we understand it. So if we want to treat osteosarcopenia, instead, and this is again my personal bias, instead of giving one drug for osteoporosis, one drug for osteosarcopenia, why not we work to develop drugs or interventions that work for both, for muscle and bone? This is something that we are trying to do, and just to give you a very quick introduction, because I know Cliff is the expert on this, but I just want to share with you a comparison when you look at aging in osteoporotic bone versus a sarcopenic muscle. I just want to highlight two things from the concept of fat accumulation, just to give you an example. We have accumulation of fat around the bone marrow, around the trabeculae, and interestingly, inside the trabeculae. In the muscle, we have fat infiltration around the fiber, and also interestingly, you look carefully here, fat inside the fiber. And we have done, in collaboration with Marco Brotto, the author of that paper that I showed you at the beginning, in Texas, we do the lipidomics of comparing muscle fat with bone fat and with other types of fats. Long story short, we found that when you compare fat in the muscle with fat in the bone, they have 92% identity composition. 92%. Different than the other types of fat. And interestingly, we found that both were more inflammatory and they were more toxic, what we call lipotoxic. How do we define lipotoxicity? Some of you work on fat, so you know this much better than I do, but basically they activate pathways that are affect, like the arachidonic acid, pro-inflammatory pathways that will affect the cells in the vicinity. So if they are inside this fiber, this poor fiber for sure is going to be affected. It's not going to function the same as this trabecula will be. So this is a summary of 15 years of our work and how we found this role of the effect of fat accumulation in the bone marrow, all the different things that are affected, like bone formation, like hematopoiesis. And then when we look at the muscle, we were really gladly surprised, I would say gladly surprised, unfortunately for the patients, but gladly for us as researchers, that they were very similar. So maybe if we can target both, we are going to be able to treat osteosarcopenia. So finalizing with treatment, we assume that what is going to work if we do the right approach, if our story is real, if we target one hallmark that is affected in both tissues, then both tissues should respond appropriately. And that's what we propose in our recent paper. We basically say, okay, maybe start looking for interventions that we are already using and see if they have an impact on both. And I know Sue will be very happy with this one and with the next one, because I'm going to talk about a little bit of exercise and nutrition as very important determinants of the biology and effect on changing the composition of osteokines and myokines, the composition of the extracellular vesicles, and the composition of the cargo from a negative cargo into a positive cargo in patients with osteosarcopenia. So we looked at, and this is something that we published a while ago. Basically, this was a simple paper, but I just want to highlight, and I'm going to go into all the components of this table, and it's not for a general, it's just for a general illustration. Basically, we looked at those clinical trials where they measured in the same population, the effect of these compounds on muscle and bone. Not in muscle separate, not in bone separately, in both muscle and bone. There are not many. I mean, the number is growing, but what we found, for instance, is that, I mean, the things that you already know about the fracture risk reduction, which is, is good for vitamin D, is not a treatment for osteoporosis, we know that. But what we're very more interested in is what some of these studies reported is the reduction in intermuscular fat and bone marrow fat in people treated with vitamin D. So we observed a change on those two types of fat. We also observe, in this very few trials, increases in muscle mass, but usually in combination with protein supplements. When we look at other nutritional supplements like protein or leucine or hydroxymethylbutyrate, we know that they reduce inflammation, increase muscle mass, increase bone mineral density. Exercise was a little bit of a challenge because exercise, people don't exercise, our patients, because they get confused. If they go to the cardiologist recommend one exercise program, they go to the endocrinologist, they recommend another exercise program, they come to me, I recommend another one. So I think that if we look at the evidence, I will not go again into all the details. I asked Laura Giangregorio, who is very well known at the University of Waterloo, about how can we come out with recommendations in terms of exercise with an impact on both, on muscle and bone, in people with osteosarcopenia. I'm not going to go into all the details because of the time, but we know, and now we are starting to do some clinical trials. We participated in one of these ones. I think it was in the Ben's one, where we treated a few people with osteosarcopenia, 100 of them, and we found increases in muscle function. So we came out with some general recommendations. Because there are not many trials on osteosarcopenia, nutrition, or exercise, we had to take the evidence that was from meta-analysis and all these different things and come out with recommendations, general recommendations to improve muscle and bone mass. But I would like to move into how are we going to move into more pharmacological approach. And when we talk about pharmacological approach, we're talking about I don't want to take too much time. I think we're still good on time. Is how we have two choices. Yeah, we either develop new drugs that have an impact on muscle and bone by targeting those good cytokines and those good, or we inhibit the bad ones. Yeah, or as a third choice, we repurpose drugs that are already in the market that may have an impact in both. And I'll give you an example. What is the most typical, most commonly used RANK ligand inhibitor? Of course, denosumab. Probably a lot of people here have used it in the clinic. Serge Ferrari came out with a nice idea in Switzerland of treating older women, postmenopausal women with osteosarcopenia with denosumab. And they demonstrated that additionally to the well-known effect on bone density, those women show an improvement in two parameters of muscle mass, appendicular lean mass, and muscle function. An interesting study, very, very well done, published in JCI, but the evaluation of these two parameters is not enough to say that RANK ligand inhibition has an impact on muscle globally. So we did another small one in Melbourne where we compared denosumab versus zoledronic acid, because zoledronic acid still inhibits a little bit, RANK ligand. So we wanted to see if it was just class specific or drug specific, and we did what a geriatrician will do to really demonstrate that these compounds have an impact on muscle. So many more functional. You probably remember SPPV, already mentioned that, but many of them. And we showed that still we found an effect, and we found more effect from denosumab, which is much strong inhibitor. So this allowed other groups to propose that maybe, I don't know, after the study, people went back. After this study by research, went back and say, maybe that's the explanation why denosumab, in the big clinical trials, show a reduction in falls. That's maybe explaining, because we didn't understand that effect at the beginning. But good news so far, bad news with this recent study. This study is from Susan Greenspan, done in nursing homes. So I just want to mention that the caveat here is that it's nursing homes. It's not performed in the regular ambulatory postmenopausal women that we treat with osteoporosis or the patients who were included in the other study. So nursing homes, they were treated with denosumab, and there was no change in any of these parameters. But again, these people are at the end of the spectrum. They already lost so much muscle mass. They are so high risk that I wouldn't expect any response. And because this is an endocrinology division, I just wanted to mention one of the meta-analysis we recently reported. We were curious about androgens, whether it has an impact on both muscle and bone. So in our meta-analysis, basically we found that after 6 months, there was increases in hip bone density, total lean mass in men, but its effects are unclear for lumbar spine. And in general, we didn't find any evidence that it really works in terms of preventing adverse outcomes associated with osteoporosis or sarcopenia, so osteosarcopenia. So, but there are not being studies done, and I have to mention that, there are not being studies done in osteosarcopenic patients, either with estrogens or with androgens. So we don't know yet what the response would be. But nothing is negative. We can still treat osteoporosis, and when we treat osteoporosis, we reduce the fracture risk. But again, this will be half of the story. So now the final part is looking to the future. How are we going to approach this? Again, I can spend here the whole afternoon summarizing all the evidence we have generated in preclinical studies, but I just want to share with you a couple of examples. Remember the fat infiltration, and just because I knew Cliff was going to be here, so this is something that we say, okay, if this fat is so toxic, so maybe we can inhibit the capacity to produce fatty acids, which seems to be the component of the toxicity of that fat. So we say, okay, let's inhibit the capacity of producing fatty acids. So we inhibited fatty acid synthase, and we treated these mice. We are osteoporotic, and they're actually osteosarcopenic, by the way, or oophorectomized mice. And this was a very simple study where we treated them with this inhibitor of fatty acid synthase, and we rescued them from the osteopenic phenotype. And when we look at the tissue, to our surprise, we observed that the mice treated with cerulean, with the inhibitor, had also increase in muscle mass. So we say, okay, this is interesting. And then we look at the muscle function, and believe it or not, we can measure grip strength in mice, and we were able to demonstrate a beneficial effect on those grip strength. However, two things to mention. One is that the levels of osteosarcopenia in oophorectomized mice are not the same as the level of osteosarcopenia in normally aged mice, first. And second is that this evidence is, to really demonstrate that this is osteosarcopenic effect, effect on osteosarcopenia, we still have to work on the effects on specific hallmarks of aging, which is something that we are doing now. Another example where we're moving toward, we're targeting hallmarks of aging. We're particularly interested on this pathway, the tryptophan metabolite, the metabolism pathway. I don't know if you are familiar with this. We know tryptophan very well because it's the precursor for serotonin, so everybody knows what serotonin is. But only 5% of the tryptophan we eat ends up as serotonin. 95% is metabolized via the kynurenine pathway. And why we find this interesting and very exciting is because through this metabolism, tryptophan plays a role in GI motility, GI permeability. We know that that is very important in mood, in sexual behavior, oxidative stress. And this bubble here is our evidence. We demonstrated that the metabolites of this tryptophan has an effect on bone and on muscle through bone turnover and metabolism. What is very important to highlight here is that in order to metabolize tryptophan, we need a healthy microbiome. If the microbiome is unhealthy, then they are going to produce bad metabolites. So tryptophan, without going into all the details, tryptophan is metabolized into kynurenine, and then it goes down until they produce picolinic acid and NAD+. And I'm sure a lot of you know about the NAD+, that from biochemistry classes, where they explained that it was very important with cell division and cell metabolism. But if you look at if the bacteria, the microbiome is unhealthy, microbiome, by the way, dysbiosis is a very important hallmark of aging. So all this is connected. So if somebody has dysbiosis, what is going to happen? They are going to have inflammation, secretion of inflammatory cytokines. When they have inflammation, it will affect cells in the muscle and bone, and they will be unable to produce the ones in green. They will stay only producing the toxic ones. And this accumulation of kynurenine and deficit in picolinic acid will produce changes such as in the stem cells, in the muscle, and in the bone, such as oxidative stress, increased marrow and muscle adiposity, senescence, cell senescence, autophagy, and alterations in microRNA. What are we talking here about? The hallmarks of aging affected by this mechanism and affecting both muscle and bone at the same time. So what about if we give the osteosarcopenic mice picolinic acid? We did that. And we observed that when we give picolinic acid, without again going into all the details, in osteosarcopenic or phorectomized mice, we regain and save them from the osteopenic profile. Now we just published this one showing the effect of the anabolic effect of picolinic acid in mice cells, C2, C12, and human cells, where we observe an anabolic effect of picolinic acid. So this is an approach that has an impact on muscle and bone. And if you don't believe me completely about the impact in muscle, then we already measured the muscle effect on C. elegans, which is a worm that we know is very widely used for aging research. And we demonstrated that treated C. elegans with picolinic acid has not only an effect on the actual mobility, muscle, but also on lifespan. They live longer. And this is the typical case of what we are going to talk on the last 2 slides of my presentation about gerotherapeutics. This is the future for us, gerotherapeutics. And we did also in collaboration with David Karasik in Israel. He treated the zebrafish with this picolinic acid, and he observed the same that we observed in C. elegans and mice. They improved the mobility and they improved the lifespan. We didn't do the lifespan in mice, but we did the lifespan in aged fish, zebrafish. I didn't know that they lived longer, that they lived 22 months. I didn't know that. But we treated those zebrafish and they move more, swim more, and live longer. So finally, where are we now? Moving into clinical trials of what we call gerotherapeutics. What is a gerotherapeutic? It's a drug, new or repurposed, that will have an effect on both muscle and bone or other tissues in an effect on several, I will rephrase that, an effect on several hallmarks of aging, with an impact on more than one tissue. Yeah? So my interest is looking at gerotherapeutics with impact on muscle and bone, because that's what I do all my work about. So this is an example of a recent paper by Sandeep Khosla, who gave to these patients what we call senolytics. So these are drugs that target senescent cells, preventing the senescence and death. And they demonstrated a small but significant effect on bone density. Unfortunately, they didn't look at muscle. And that's my conversation with Sandeep all the time. Why you didn't measure muscle in these individuals, but I hope they were going to do it in the future. But now we are running a few clinical trials, testing some interventions. This is a collaboration that we have with the Buck Institute, with Ohio State University and the University of Connecticut, and McGill just joined this NIA-funded study, where we are giving people with osteosarcopenia, we are giving ketone ester, and basically it's an intervention that instead of focusing on the intervention, we're focusing on the effect on not only on the function and the other mechanism, but on the hallmarks. Which hallmarks so we are taking muscle biopsies, we are taking many different tests just to look at the hallmarks. Another study that we're doing at this moment is the EMPIRE study. This is something that we're doing with Dan Kirk. I mentioned him several times because he's the key author in many of my papers, or our papers. And we are giving them vitamin D alone or in combination with HMB in osteosarcopenia. Again, not necessarily to show that it's going to prevent fractures, it's going to have an improvement, is to understand how these drugs may have an impact on the hallmarks and then try to develop from there. The other thing that we're working on is looking at the potential for extracellular vesicles and how we can use these extracellular vesicles to treat bone and muscle. So we try to look at the cargo and see which ones have the good cargo, and then multiply them and reinfuse. Now we can have at McGill and other centers, of course, but at McGill we have the capacity to build up our own extracellular vesicles a la carte, which means that we can order whatever package we want to be the message, and they will do it for us. So this is probably the future. But in the meantime, while we are working on this, this is my left phone message, I would say, is if you have your main interest is bone, or you see osteoporotic patients, please look for a partner with muscle interest, or integrate muscle as well, and vice versa. You work on muscle, please think about your bone partner, because I think that's where we are going to move in the future. And this is what we recommended here in this algorithm of what to do in clinical practice. I run a falls and fractures clinic. We don't run separate clinics. We think that the falls and fractures integrated clinic is the best way to go in terms of clinical models for people with osteosarcopenia and fractures or sarcopenia. So in summary, I will not repeat all this, but I can tell you that the bone and muscle relationship goes beyond mechanical. I hope I've convinced you. And I think that we are going to use these combined interventions now and in the future. So with this, I would like to thank all my collaborators. This list of collaborators is limited only to the evidence that I show in this presentation. So, but I think that we have a nice network of collaborators all over the world. I would like to thank my main team at the center and all the people who pay the bill for supporting these studies. Thank you again for your invitation. Thanks for your attention. I'm more than happy to discuss and answer to your question. Thank you very much.
Thank you, Dr. Duque, for a very interesting talk. My name is Caroline now from the Department of Biosciences, and I'm here to lead the question and answer period. So if you have a question, see me. I'll hand the microphone from phone. Questions? Yeah.
This is really exciting. I was very amazed to see your exosome works. One of the also you mentioned when you're going to target exosomes to treat the diseases. So on the issue of exosomes, is the exosomes carry particular receptors. And that's what lead to avoid specificity and stuff. So how are you going to, what kind of exosomes, if you use all artificially made, then you need an issue, or you have an issue that putting that protein receptor. How are you going to do that?
Yeah, that's. I mean, the way we select the cargo, you mean, the way we select the cargo, we are using two approaches. One is, well, there is a lot of people now publishing about this, and we take from the results and try to look at what extracellular vesicles are the best. But at the same time, we grow cells. We grow the mesenchymal stem cells, for instance, healthy ones, from young individuals, and we identify we extract the extracellular vesicles in the supernatants, and then we treat bone and muscle cells with those, or even fat cells with those supernatants, and we see, I mean, very simple experimental approaches, and at the same time we dissect them. And that's the advantage, where we can do microRNAs, microRNA arrays, or determine, the biochemical composition of those cargo, and then we can identify which factors are based, which one we select based on the response from those cells. The advantage of doing it a la carte means that we can order, we say, okay, microRNA 1B, for instance, we want that one in the content. But we want the content also to be a osteocalcin, to say something, just to give an example. Then they pack it for us, but they also have the capacity to identify antibodies or that goes to the specific targeting. So we target in muscle. So we send that cargo, with osteocalcin and the microRNA that we are interested on, and we look at the response. That's a little bit more in the future. But at this moment, where most of the evidence from my lab, but I know other groups have already moved into in vivo. From my lab, we are moving into from the bench to the translation. Thank you.
Thank you very much. So if I consider all the different pathways that are impaired in sarcopenia, it reminds me very much of what we see in obesity and diabetes. There are all these, whether it's autophagy or epigenetic changes, etc., etc. And overall, this is mostly a reflection of impaired health, I would argue. So what do you think is the initiating, and obviously that's the 800-pound gorilla in the room. So what triggers all this? What is it about aging that does all that?
Yeah, this is an interesting question, and I can tell you, yes. There is a similarity in terms of the activated hallmarks in compared with obesity, but definitely the hallmarks that we observe, despite they are similar, they behave differently. And they behave differently in obese versus diabetic patients versus osteosarcopenic patients. So it's not that unique, and that's the same in cancer. I mean, although some of these hallmarks were taken, the idea of the hallmarks was taken from the cancer field. And then they were adopted by the aging field. Coming back to your question, I mean, what triggers this? I mean, I think the only factor that we know triggers this is age. So, and the age, more and older we get, and we think that this, and that's becoming a concept that we call intrinsic capacity. Yeah, so intrinsic capacity is the sum of everything that we have in our biology that protects us against stressors and decline. So if we reduce that intrinsic capacity, it's associated with, I mean, it's all the protective mechanisms that prevent those hallmarks to be affected. So if we are, because we observe, and that comes from the super aging people, people who survive 90 and they still run marathons, so that comes from them. What prevents them to develop that is they still keep, first, risk factors absent, yeah, and they keep a healthy lifestyle. That's probably what keeps the intrinsic capacity and keeps all the protective mechanisms from, from being reduced. So I'm not limiting my speech to, diet and exercise because everybody will say, okay, this is good, but it's because these biological protective mechanisms, and also 50% or about 40% is genetics. We know that the longevity genes are transferred from women to through generations, usually like women. So if my mother lives 90, I will be most likely, if I don't drink, I don't smoke, to live 90. But that's very variable based on the environmental factors that represent 60%. And you know what the difference between environmental and genetics is. Yeah. So if my son looks like me, that's genetics. If my son looks like my neighbor, that's environment.
This somewhat relates to the question that Christoph just asked you, but I wanted to ask you, there's a certain threshold where the treatments no longer work. You showed Susan Greenspan's work in the nursing home, and that related to the question. And the reason why I'm bringing that up is in the nutrition field, we have this nutrition support, enteral, parenteral, and there's a certain point where, oh yeah, they gain weight, they gain muscle, they never measure bone. But they don't get better, and people argue about it. So I just wanted to bring that up to you. Is there a threshold, or is this something that you think about where they're over the edge and we can't treatment them or help them?
Yes, this is a very interesting topic because yes, there is a threshold, and that's something that we are working now. And it's called we call it the Thrive project. Coming back to the previous question about intrinsic capacity, I'm talking about intrinsic capacity, because it seems that there is a moment on intrinsic capacity where the person is not going to respond anymore. And that will be an important determinant of the medical decisions, clinical decisions, ethical decisions, and also clinical research. So we don't expect, for instance, and this is so that somebody with an intrinsic capacity of 10% is going to respond to exercise and diet. But this is a speculation at this moment, because what we are working on with this is 15 cohorts worldwide with 12 countries. And we are measuring intrinsic capacity in about 300,000 people. From cohorts that are already completed, including the Canadian Longitudinal Study in Aging, which is 50,000 people. So we want to measure intrinsic capacity as one indicator of the some people call it resilience, but I don't like that term of resilience in older person, but it's basically something that we can measure, quantify, and we are now correlating it with the biological markers. So it's not only the level of function or cognition, mobility, or mood or sensory, but also how it correlates with the specific markers and how it correlates with these indicators. When in the preliminary analysis that we do the Thrive study, which is funded to our group by the CIHR, the equivalent to NIH in Canada, our preliminary analysis indicates that probably the musculoskeletal system is the most important determinant of intrinsic capacity, because it's all the components of intrinsic capacity, and we had a big surprise when we found evidence that some proteins secreted by muscle could have an impact in cognition, and not vice versa. When we think about dementia, we think how dementia people develop sarcopenia. The paradigm, as the old paradigm of the mechanical thing, was that okay, they walk less, they eat less, therefore they develop sarcopenia. And now we find that is not the case. It's more sarcopenic you are, more plaques you have in your brain, and more dementia the person has. So we're changing those paradigms. And I know I'm completely biased because all my life is around the musculoskeletal and aging, but we find that connection. Even hearing, very good evidence of people with osteoporosis have lower hearing. And now we know that people with sarcopenia also have lower hearing compared with people without osteoporosis. How do we explain that? Well, there are muscles and bones in the inner ear. They're small, tiny, very, very, but they are also affected by the same conditions with the same triggers of the same.
Very nice. Thank you for a wonderful talk. I don't know if there's anybody else. If we have to end it now. Dipak. Oh,
Okay.
sorry.
Thank you very much.
Yeah, we will do that for a speaker. So we'll have a parties or break to have coffee, and then we'll have the next one. I'm going to call up Shapses, who is a professor of nutritional sciences and director of Next Center at the NJ-IFNH. Sue.
Okay, hi everyone. It's a great pleasure to be here today and have it focused on bone and muscle, and to be the one introducing Cliff Rosen. So I'm going to look and see. Okay. I just wanted to see the name of your talk, but I'm not going to name it. I'm just going to tell you that Dr. Rosen is the Director of Clinical and Translational Research and a Senior Scientist at Maine Medical Center. He has a big lab of 11 people. He has 660 publications. He has over 30 years of NIH funding, over 30 book publications, and his focus is on bone cells and fat, and it brings together, I always remember his first meeting when he was going to do, and he did an adipocyte meeting at the bone meeting, and some of my adipocyte friends said, "Who is he and what is he doing?" And I said, "I don't know, he's just dabbling." Well, he wasn't dabbling. This has been his field for the last many decades, and he has advanced the field, and it's very interesting. I know that he's been a leader of so many different groups. I'm going to mention SBBT. This is his NIH Chair of Skeletal Bone and Biology. He also was chair of a committee that I was involved with, and that's how I really met Cliff, when he was chairing the Vitamin D and Calcium Dietary Recommendation Committee. And we had a great time together. Everyone seemed to not like us at the time because there was so much controversy. And one day Cliff just said, "I think we should all just get bulletproof vests and be fine after that." So that's his sense of humor. I met him in Lausanne, Switzerland, a very long time ago, but I always remember when he was president of ASBMR because he set up a skating event, and it was so much fun as a fan of winter sports. And I saw Cliff going around like a pro, faster than anybody else, and I just said, "Whoa, that's the president who just flew by." So he's a lot of fun. He's great to talk to. We've had lots of conversations. He still runs 5 miles a day, now that I know that, even this morning. He's a reminder that energy and excellence can go hand in hand in science, medicine, and beyond, and that's probably all I'm going to say, except that it's such a pleasure to have you here. Okay.
I don't even remember that. Thanks, Sue, and it's great to see people here, some old colleagues and friends and some new people, and just a shout out to Nikki, my role model. I finally found somebody who isn't going to retire either. That we keep going. This is really fun, and thank you, Dipak, for inviting me as a pioneer. And I want to start by doing something a little different, and thank Gustavo for his great talk. And you'll see that that we have some overlap. It's hard to get this screen here. Okay, so I want to talk about a pioneer that many of you may not know about, but he was the second dean of the New Jersey Medical School, and his name was Rulon Rawson. And he was an endocrinologist back in the days when endocrinology was really very early in it. Both, we didn't have a fellowship, we didn't have people, young people in the lab. There were a few centers that were excelling in endocrinology, and Rulon's work was primarily on thyroid. He did a lot of work on radiation-induced thyroid disease, and also radioactive iodine as a therapeutic. So why do I bring that up? Well, one is I wanted to see, I hadn't been to New Jersey since I was 14 years old, so I wanted to see what the medical school was like. And secondly, because I actually had a connection with Rougon. So in 1966, a year before he became dean here, I applied for a summer position in a lab, and I applied to the Jackson lab, the lab in Buffalo, and Rockefeller. And I didn't get into any of them. Of course, I was only 15 years of age, but it was my first disappointment in terms of competitiveness. But I got a letter from Hutchinson River Boy Scout camp, and they said, would you like to come? We heard you were accepted, but you know, we're a second organization, and we'd love to have you attend summer camp, summer science camp. So I said yes, and my parents were grateful enough to get rid of me, that I went from Utica, New York to Pawling, New York, where the Hutchinson River Science Camp was, and Rougon ran it. And he brought in all these guest people who were stars in their field. I can't even remember some of them, but I remember Rougon and his wife, Jane, who was the mother for all of us at 15 years of age. You can imagine we're doing experiments on rats in these tents next to the Appalachian Trail. And a lot of us were very anxious. My roommate was somebody from France, Pierre, and it was my first experience, and it was absolutely wonderful. It was the chance to see science in action, plus we used to hike in the Appalachian Trail. And so just a shout out to this connection that brings me back to the fact that after that, I met one person at camp that invited me down to New Jersey for a weekend visit, and that was really exciting and fun, and that was the last time I actually spent any real time in New Jersey. So with that introduction, and the fact that your medical school is growing and becoming actually going to consolidate into the Helix building is really a testament to how things have moved in the field and in the science, and particularly at this institution. So what I'm going to do is talk a little bit about weight loss-induced bone loss and focus on first just a primer on skeletal morphology, talk about weight loss in humans, the evidence for bone loss, and then weight loss in mice and the clinical implications. So very briefly, our lab has been interested in the last few years in understanding the skeletal response to weight loss. And this has huge implications. The GLP-1s that have come into existence with this great levels of enthusiasm and efficacy. And every week, I was telling Christoph, every week as an editor at New England Journal, I get a GLP-1 paper. I just got one last night in the middle of the night, another one, and I can't remember now what it was on, but, GLP-1 and thyroid cancer. And last week it was GLP-1 and alcohol dependency. So these drugs are going to be used widely. They're very efficacious, not just for weight loss and for control of diabetes, but we're involved in long COVID studies with the NIH, and we've been working on long COVID and fat tissue for the last 5 years. And the GLP-1s will be introduced as a clinical trial in the near future to treat long COVID. So these drugs are out there, they work, they're effective. The question is, what happens to the skeleton and to lean mass and bone mass when these drugs are used? So it's very timely. And in our lab, even before the real explosion of the GLP-1s, we were interested in this concept, and Sue has an abstract at this meeting that talks about weight loss-induced bone loss and the response to different agents. And we were really asking a very simple question. Is this just skeletal adaptation? Does the body just adapt to weight loss because there's less gravitary forces? So the skeleton continues to model itself in response to what your body is? Or is this a pathological condition in which there really are changes that are occurring that are not meant to be changing, and or are these compensatory mechanisms that really override a physiological process? So that's where we're at, and for most of us in the bone world, we're called boneheads for a reason. When I bring this up, people say, oh, you know, it's skeletal adaptation. This is very clear, and we get this in the study section as well. Well, it's obvious that the skeleton remodels in response to weight. Well, I'm going to go through some of the questions and try to answer that, and I'll give you a preview that the answer is not as clear-cut as we hope it would be. So let me just start by talking a little bit about skeletal morphology, and just to remind you, the cortical skeleton really is important for protection. It's high impact protection, and it's a very important part of our skeletal modeling that occurs with growth and development. Trabecular bone, which comprises about 10% of the skeleton, is, you know, within the bone marrow compartment, and is much more related to repetitive loading, and it's about 5% of the mouse skeleton. So it's not nearly as large a component, but it has very important metabolic functions. And then the periosteum. So Gustavo and I do a lot of similar work. So this slide is not surprising. It's the same slide that Gustavo showed, only a little bit more, less detail than he had. But I wanted to focus on periosteum because that is the source of skeletal adaptation and modeling that occurs with growth. And it turns out that it's a very important but less well-studied part of the three components of bone: cortical, trabecular, and periosteum. And it's composed of both the outer fibrous layer, which is what is connecting to the tendon, the inner cambrium layer, and then of course the cortex. And so with changes that occur with loading are going to affect the periosteum. And so understanding how the periosteum functions is very important. And you may know that if you break a bone, especially a long bone, the pain fibers are really significantly activated. And so it's a highly enriched source of nerves, but also the vascular component. And type H vessels, as well as regular vessels, are permeating particularly the inner cambrium layer, but also to a certain extent the outer fibrous layer. And as one might predict, the cellular composition and the cellular behavior of osteoblasts in the cortical skeleton is different. Nikki was just telling me about how she's isolating calvarei, and the calvareal osteoblasts are clearly functionally different than osteoblasts that are sitting in the trabecular bone. So understanding that compartment is very important, and I'm going to come back to that in a little bit. And then, of course, we've got the marrow compartment with the trabecular bone and the assorted cells that are regulating each other. As Gustavo showed, there's a tremendous amount of intercellular communications, and we'll come back to that. So what's the clinical evidence for weight loss-induced bone loss? And it's pretty substantial. We started about 25 years ago with Ann Klebansky, who's now the CEO of MGB, Mass General Brigham. So she's out of the business and into another huge business. But anyways, we started with looking at anorexics. And she was a pioneer in the field early on in describing the low bone mass and fractures that are a component of this psychiatric syndrome. And it turns out that we reported that these individuals also had increased marrow fat, despite the fact that their fat was almost gone in the peripheral part of their body. So that was a very paradoxical finding, and something that really led us to ask the question, what is marrow fat doing in a situation where you really have virtually no fat? And you can come up with 100 different hypotheses as to why that might be. And we'll come back to that as well. But the anorexia model is complicated. So they have amenorrhea, the physical activity is different. Some are super hyperactive and others are not. And there are a number of other components that including CNS components that make it very difficult to use it as a model system. But we have other evidence that weight loss causes bone loss. And that is the look-ahead study in type 2 diabetes, where not only did they have substantial bone loss, particularly in the first 3 years, when these individuals were randomized to an active education and diet regimen, but also an increased risk of fractures. And so that suggested to us that this may be a very real phenomenon that is more than just skeletal adaptation. And then, seminal work from Kristen Beavers and others, and from the study of osteoporotic fractures, it has shown that presents through that in observational studies, with about 10% weight loss, you get about a 1 to 2% rate of bone loss from the hip. And some of the studies have suggested, this is from Chris Beavers in 2014, that exercise may ameliorate part of that effect. You'll hear, if you go to Sue's poster, that maybe time-restricted eating may be something that modulates this effect as well. But I think the evidence is starting to become more overwhelming that calorie restriction causes loss. And then there's a paper that few people remember that Chris Beavers looked at, and she was asking the question, what happens to bone after weight regain? So you lose weight, but then many people fail on their weight loss regimens, and so they regain their weight. And it turns out that these individuals do not gain back their bone. So this suggests to us that there may actually be a more pathological component to weight loss-induced bone loss. Because if it was fully gravitational, then one would expect that return as weight loss goes away and you start to regain weight. And this becomes really, really important for the GLP-1s because these people are getting on it and then they're getting off it, then they're getting on it again. And we've ignored that in our lab and just starting to look at that yo-yo phenomenon. I'll come back to that in a minute because it may be very, very important. So the other study, and probably the best study to date on calorie restriction, the longest, but in individuals who were normal weight and healthy, is the calorie study, which was funded by NIA back in 2004 and run by the group at Duque, Bill Krause and his colleagues, and I happen to be chair of their steering committee, so I've become intimately familiar with not only that study, but their legacy study of bringing them back in, these individuals who were targeted for 25% weight loss over 2 years. The people didn't make 25%, but they made about 18% in the first year, and then about 9% in the second year. That is, their appetite began to rebound after the first year, which is a very common phenomenon in weight loss studies that with calorie restriction, is that as you lose or restrict your calories, you lose weight, but your appetite begins to recur. And this also happens in mice as well. Anyways, the bottom line was that there's tremendous metabolic benefits to calorie restriction. So much so that 2 new studies from NIA, if NIH actually gets going, is going to look at that in a more long-term follow-up. And we're all kind of excited about that calorie restriction studies because of the longevity promise and also the fact that the metabolic indices are impressive. But there is a problem, and that is, at least during the first 2 years of the calorie study, there was significant areal bone loss in the range of 1% per year to 1.5%, even as much as 2% at 2 years. And whether this continues or not is really important because it raises a whole question about how calorie restriction can be used as a therapeutic potential. Sue's study suggesting maybe time restriction doesn't do that, and I'm involved in a couple of DSMBs that are looking at time-restricted eating, and it may not cause that same degree of bone loss, but it's a very important element of a therapeutic intervention that we're all endorsing. We know that gastric bypass also causes bone loss, and this is very dramatic and more common with Roux-en-Y gastric bypass, but also occurs with the sleeve of vertical sleeve gastrectomy. And as you can see, and I was encouraged to see that Sue also reported that with calorie restriction and also with gastric bypass, that you get radial bone loss. So the radius is not a gravitational site, so if you're thinking that it's all about gravity and this is physiologic adaptation, then something's not quite right, because the radial bone loss is very consistent with a non-gravitary force on the skeleton. And there's an increased risk of fractures with gastric bypass. So what about the GLP-1s? So the meta-analyses suggest that there's either no effect or even a slight protective effect from primarily observational studies. One problem with the GLP-1s, is the companies own the data and the studies. So they don't want to do the bone or lean mass studies. They don't want to give you drug unless you buy it at full cost, which is, and I'll come back to it at the end, very, very expensive to do a trial, an NIH-funded trial, using any of those agents because of their cost prohibitiveness. But to Novo's credit, they did this study, a secondary analysis study, looking, and also with tirzepatide, but not published, from Lilly. But in the Novo group, they were able to show that bone loss occurs with the GLP-1s in a one-year randomized trial, looking at either liraglutide, and also the same thing occurs with semaglutide, that the degree of bone loss is fairly consistent, particularly in the hip, less so in the spine, and exercise has a very, very modest, if any, effect on attenuating. In addition, also something that's not as well known is the FDA added a label for fracture risk in semaglutide treated individuals, and there was an increased fracture risk in both women and people over the age of 75. There were on the large studies of over 5,000 individuals treated with Wegovy, which is semaglutide. So there is some evidence that this is more than just inconsequential bone loss. And then in a recent paper by Hansen and colleagues, they looked at micro-CT analysis and found that cortical bone was reduced in those individuals who were treated with semaglutide. So, calorie restriction in humans causes aerial bone loss in the appendicular skeleton, and I believe in the radius as well. In humans, bone resorption is the major feature of calorie restriction-induced bone loss. I didn't show the data, but CTX, as Gustavo showed, is a good marker of bone resorption, and that is increased with calorie restriction. And bone loss occurs with gastric bypass and GLP-1s. And long-term calorie restriction may potentially lead to an increase in fracture risk. Okay, so we were interested in, this was several years ago, in understanding what the mechanism of this calorie restriction-induced bone loss really was. So we started with black 6 mice, and we just performed routine calorie restriction, 30% calorie restriction in black 6 mice. And you can see, that they have this significant weight loss. It's about 20% weight loss. And at the same time that they have weight loss, both males and females, males in blue, they have lower serum IGF-1 levels which is consistent with the reduction in calorie intake, and we'll come back to that in a minute. Their skeleton is altered. So what happens is that you have a significant degree of cortical bone loss. And so you get cortical thinning that's somewhat symmetrical, and that relates to the reduction in humans in DEXA. When you measure by DEXA, you're basically measuring cortical bone is reduced. You see it both after 4 weeks and after 16 weeks as well. It's really remarkable cortical thinning. The interesting thing is trabecular bone is preserved. And we've been trying to understand the nuances related to these differences in skeletal compartments, because we believe, as a preview, that much of the cortical bone loss is occurring on the periosteal envelope. And that would come back to this idea that there's less force on the outer edge of this cortical bone that's reducing the skeletal size. And this occurs in young and old B6 mice. It occurs also in different inbred strains of mice. So this is a fairly universal phenomenon, at least in mice, and probably so in humans. So when we look at the basic underlying mechanism of this bone loss, it's a little different than in humans. And this is where we get hung up a bit, because we can use it as a model, but whether it translates directly to what we see in humans is another question. But you have profound suppression in bone formation and bone resorption. So the entire remodeling unit is suppressed, and this ultimately leads to an impairment in the acquisition of bone. As mice age, they still grow bone. It's very slow, but in response to calorie restriction, the remodeling unit is totally shut down. And the biggest impact is in the periosteum, where you get absolutely no double label, and you get this marked suppression in bone formation. And so these animals, if you would think that as they lose weight, they're getting skeletally adapted, then they would remodel their skeleton to make sure that they're fitting their weight. And that's not the case. They are saving their bones by reducing their metabolic requirements. So they're shutting down bone turnover totally. So there are two features about this that are unique in the mouse, and probably in humans as well, but that we need to prove. The first is that at the same time you have a reduction in the cortical shell, you have this increase in trabecular bone in the cortex, which we call trabecularization. Now, Gustavo may recognize that because it's a characteristic feature of the aging human skeleton that you get this trabecularization. And we've been trying to understand the mechanism related to that. It could possibly be that as you slow resorption so much, the formation actually exceeds resorption in the trabecular skeleton and in the endocortical end of the cortical skeleton. But anyways, it's a fairly persistent feature that we see. And then the second thing we see, I guess it's cut off here, but you can sort of see a little bit. This is the cortical shell in the longitudinal nature, and it's thinner, but the trabecular bone is pushing right up against the endocortical envelope. And then the second thing, as Gustavo mentioned, is bone marrow fat. And here you see this tremendous increase in marrow adiposity. And this occurs quite early. It's quite reproducible, whether it's fasting mice or calorie-restricted mice. This event occurs, and it's dramatic. And so this raises the parallel with the anorexic model in humans, in which you see this tremendous increase in bone marrow adiposity. So what possibly could be the reason for this? And as Gustavo mentioned, bone marrow fat is unique. The cells come from cells that are actually progenitors that have some skeletal features as well. And so in our laboratory, and some work I'm not going to talk about, but we published, in E-Life, we showed that at least in calorie restriction, this increase in marrow fat may be compensatory as a means of allowing osteoblasts to have a local source of energy. Because as I told you, the whole system is shut down. And so it needs available fatty acids to continue to have any kind of osteoblast function. So it's a whole separate topic, but it's an interesting one because it challenges the model that all marrow fat is bad for the bone. And we were able to actually delete ATGL, which is a major lipolytic enzyme, and show that with that increase in trabecular bone is lost. So they lost their one protective mechanism for preserving the skeleton. Okay, so we show this data and we show it in grants, and then people say, oh, well, that's not comparable to what we do in humans, because it's really obese individuals who undergo calorie restriction. So what happens with calorie restriction after a high-fat diet? So this is work from Carolyn Shevik in our laboratory, who came from Cornell and is really a biomechanical engineer, but she was very interested in this question of skeletal adaptation. So that's a design, and you can see both in male and female animals, they lose a tremendous amount of bone, even though they had a high-fat diet to begin with. So weight in general increases areal bone density, although high-fat diet is inflammatory to the skeleton. When you calorie restrict these individuals, you get that very same feature, and particularly in the periosteal skeleton, you get this tremendous suppression in bone formation and decreases in mineralization apposition rate. So what are the mechanisms that lead to this compartment-specific bone loss with 30% calorie restriction? So we, Wendy, I hope she's still here. Do I see Wendy? There she is. Okay, so we were talking about that yesterday. Wendy and I come from the IGF world. That's where we were sort of born and grew up. And about 15 years ago, when my next competitive renewal study section told me, we all know everything we need to know about IGF and bones. So go on to something else. You got to be agile in this business. It's not something that you can just stick with one peptide. So anyways, it was lost and forgotten and put away, and people hadn't talked about it. And during this time when Carolyn came and we were discussing the skeletal adaptation, and it was in Gustavo's slide, of course, that muscle is a very common source of IGF-1. It's also a very anabolic to muscle and to bone. The problem is it also increases bone resorption. So it's never been used as an anabolic agent directly. But we do know, and this is work from Nikki and others, that PTH drives IGF-1 locally in osteoblasts, and certainly has a significant component of its anabolic properties or IGF. So we went back to look at our anorexics and the data there, and you can see that this is work from Miriam Berdella, as general now at NYU, that showed that radial failure load in women with anorexia is directly related to circulating IGF-1. So that's indirect evidence that IGF-1 may have some impact on the periosteum and on the cortical skeleton. So 25 years ago, Derek and I and Shoshana Yakar did an experiment where we knocked out IGF-1 in the circulation using a primitive albumin promoter and showed that serum IGF-1 levels went down. So that was the primary source of circulating IGF-1 was from the liver, but also that it had an impact directly on bone growth and density. And what was that impact? At the time, we weren't thinking compartment-wise, but when you go back and look at the data, it's all in the cortical skeleton. So this gave us some hope retrospectively that one, that we need to think more about compartment-specific changes, and two, that IGF-1 may have an effect. So what Shosh did as subsequent follow-up was to use a conditional deletion of IGF-1 in liver, and showed that at 1 year of age, you get that reduction in serum IGF-1, but you also get to see that it's not just growth, but skeletal maintenance is also impaired. And so the cortical adaptation is reduced, and you have a smaller cortical shell. And this is principally where the IGF-1 action is. It's inhibition of periosteal expansion. So with aging, one of our adaptation mechanisms is to increase your periosteal envelope in response to loss of trabecular bone. So if you think about it as a donut, and then the inner compartment is being lost in the trabecular skeleton, that's where most of the age-related bone loss occurs initially. The compensatory response that the skeleton has is an increase in periosteal expansion. And that's a really important component of why 100% of us don't fracture, because we have this element of being able to compensate. Well, when you knock out IGF-1, you lose that compensatory increase. Oops. So we looked at that just in a simple regression studies in our calorie-restricted mice. And as predicted, no big surprise, but the serum IGF-1 had a strong predictive value in periosteal apposition. So the lower the cortical shell is, the lower the serum IGF-1. And it accounts for 50 to 80% of the variance. So that sounded good, but it was correlational. So we turned to mouse models that we can genetically manipulate. And in our lab, just over the past couple of years, we've only been able to focus on the periosteum. We got a lovely new postdoc from Penn, who did a lot of work on periosteal changes with fractures, and she's a superstar. She came to our lab and immediately changed all our attitudes about the periosteum. Anyways, so one of the things that Anyanya Gunter in our institute has been doing is been looking at conditional models that work with the periosteum. And we know that PRX1 labels about 10% of periosteal cells that are osteogenic in green. And so he was able to show that when he conditionally deleted IRS1, which is downstream of IGF-1, he was able to show that there was a significant reduction in cortical bones. Cortical skeleton is reduced, and again, very consistent with what we see with calorie restriction. When he did the double knockout with the PRX1, you get this tiny, tiny bone. So you can see that the cortical skeleton is extremely sensitive to IRS1 and IRS2 reduction, suggesting IGF-1 and potentially insulin, which also works through IRS1, may be involved in that skeletal changes. So that's sort of good evidence that IGF-1 is important for the skeleton, but particularly for cortical bone. So with that information in mind, we went back and asked the question, is this occurring with semaglutide? So Carolyn, in her model systems, individually fed the mice a high-fat diet, 60% calorie, high-fat diet, and then treated with either calorie restriction or semaglutide or no treatment at all. And then we had a control group. So when you look, and this is a somewhat complicated slide, but I'll just take you through. Basically, what happens is male animals that are treated with semaglutide have markedly reduced cortical thickness. And again, this is the size of the sort of donut, the size of that cortical shell that's reduced. This is fairly consistent in males, but not in females, which is interesting, and she's exploring the sexual dimorphism. But in addition to that, they have low IGF-1s. And so this would suggest that IGF-1 is indeed having some effect on the cortical shell. Okay, so in addition to a reduction in bone with semaglutide, you see this reduction in lean mass as well. And this is what we see in humans, that there is 5 to 7% reduction in lean mass in GLP-1 treated individuals. We see the same thing in mice, but it did not correlate with functional muscle changes. So whether this represents some unique feature of the GLP-1s is unclear. We certainly see it with calorie restriction as well. And as predicted, at least in males that have the lower IGF-1, they have reduced bone strength. So this would be consistent with the hypothesis that IGF-1 is playing some role in changing the skeleton in a negative way as calorie restriction or semaglutide is being treated. So what's going on? I told you already that there is this tremendous reduction in bone formation. And I think the mouse, anybody who's worked with mouse knows they are tremendously compensatory. Anything you do to them, they can figure it out. They can go back and do anything they want to make themselves still alive. And so we think that this suppression in bone remodeling is just due to conservation of energy, that they're trying to conserve energy at all costs. 30% calorie restriction is a big deal for these mice because they love to eat. And so we wanted to try to understand what was happening at the metabolic level in these animals. So in these individuals with that went high-fat diet and then went to calorie restriction, we looked at the metabolome using untargeted metabolomics and showed that it's now actually just got accepted for publication in Bone, that high-fat diet changes the metabolome, and then calorie restriction, as you might predict, also changes the metabolome in a different way. And when we do spatial metabolomics, this actually provides some interesting information about what's happening at different levels of the skeleton. And Carolyn is particularly interested in this because different parts of the long bone respond differently to gravitaric forces. And what she showed, and this is a paper that just came out, is that during 30% calorie restriction, there's reduction in de novo lipogenesis and impaired amino acid conversion to pyruvate. So what does that mean at a cellular level? And this is work that was just recently published by another person in our lab, Lin Liu, another postdoc. And he showed a rather dramatic reduction in oxidative phosphorylation in the cells, the bone marrow stromal cells that are undergoing calorie restriction. So, no surprise, they are metabolically compensating for their lack of energy, particularly by an impairment in their ability to mitochondrial oxidation and some component of glycolysis as well. And interestingly enough, when you take those cells and grow them as fat cells, same progenitors grow them as fat cells, they actually have increased production because the shift into higher reactive oxygen species actually favors adipocytes. So that metabolic switch is what's happening at the cellular level, and that's why we see increased marrow fat, and that's why we see this reduction in cortical bone. So cortical bones preferentially lost, suppression of bone turnover, periosteal changes in relationship to IGF-1s are clearly important, and the GLP-1s can lead to reduction in bone strength, possibly due to their impairment in cortical bone. So what's happening in trabecular bone, and what's going on with that trabecularization? Well, one thing we know is that there's an increase in marrow fat, and trabecular bone is preserved. So we went and did an unbiased analysis of bone marrow, which included progenitor cells as well as other cells. We have single cell data later on, but when we first did this, it was just bulk RNA-seq. And what we found was that one factor was predominant, and that was complement factor D, or adipsin, which is a adipokine that's released by fat cells. And this was increased in mice that underwent calorie restriction also increased in aging mice. So we aged them to 18 months, and there was increase in marrow fat, and adipsin showed up. So I just want to tell you about these parallel tracks between aging and calorie restriction because they feature a lot of the same things. There's cortical thinning, there's trabeculization, there's increased marrow fat. So when we think about human aging and what it's doing, we have to also think maybe some of that is compensatory, maybe it's some response, or maybe it's similar because there's less calories. So anyways, lots to think about. So when we looked at whole bone RNA-seq, what we find is that complement factor D, a whole marrow, complement factor D by qRT-PCR is increased consistently. So what is complement factor D? So it's part of the innate immune system. It's a component of inflammation from the complement system. So it's made by adipocytes, but it's a complement factor. And so it's really essential because it binds the complement factor D to induce the complement factor C conversion to C3A, which becomes important for not only activation of immune response, which is shocking to think of calorie restriction as an immune response, but I'm going to show you that data soon, but also it has impact on the mitochondria as well. So to address what complement factor D was doing, we did some in vitro studies, and clearly it suppresses bone formation. And when we globally delete it, you get this increase in TCF1 and some of the factors that are important for osteogenesis, as well as reducing marrow adiposity. Turns out adipsin is also made by stromal cells that end up being osteoblasts, so it's not just adipocytes. And we think Wnt signaling is the major component of this change. So adipsin suppresses Wnt signaling, particularly the non-canonical pathway, Wnt16, and other canonical Wnt pathways, but primarily Wnt16, which has been reported to be an important component of cortical bone. So it might fit very well with our hypothesis about cortical bone. So when we globally deleted complement factor D, you get a reduction in marrow fat, you get an increase in trabecular bone. No surprise, I guess, because it's such an important adipokine in the marrow environment. But global adipsin deletion also deletes in peripheral fat, and there, peripheral fat, adipsin is important for insulin sensitization. So adipsin was one of the first adipokines described in the late 1980s by Bruce Spiegel. So we really needed a bone-specific or marrow-specific conditional deletion. And so we used the PRX-CRE, which is expressed in bone cells, but also in early adipocyte progenitors in the marrow, and showed that PRX promotion of impairment in a complement factor D rescued the skeletal phenotype of both males and females. And interesting, and we don't have an explanation, and we're working on it, but we presented it at the bone meetings this fall, and everybody asked, so why is IGF-1 rescued, serum IGF-1 rescued by a conditional deletion in bone of complement factor D? And we don't have the answer to that. But it goes along with the fact that the skeleton has been restored in response to the impairment reduction in PRX. And interestingly enough, that trabecularization also goes away. So you rebuild the cortical skeleton with this rescue, and the trabecular increase then disappears. So what does all this mean, and why is it important? Why do we even think that these mouse experiments give us any idea about what's happening in humans? So Sam Costa in my lab, who's now at the University of Pittsburgh doing a postdoc, and I and Ann Klebansky and a few others decided to test this in humans. And so we recruited 25 individuals. We paid them $7,000, and we asked them to go into the clinical research center at the Mass General and sit for 2 weeks with fasting, 10 days of fasting. And we also said, but we'll also give you 10 days of a high-fat diet. So when we designed the original study, we wanted to fast them first and then give them a break and then reward them with a high-fat diet. But none of the individuals wanted to be fasted first. They wanted a high-fat diet. So we went with a high-fat diet for 10 days, gave them a break, they went home, came back, and then were fasted for 10 days. And the bottom line is they lost weight when they fasted, they gained weight when they ate a high-fat diet, and in between, they neutralized everything. But what was remarkable is just 10 days of a high-fat diet or 10 days of calorie restriction is fasting, bone marrow fat went up very immediately. And this gave us some clues, both with a high-fat diet and with calorie restriction. So Sam Costa asked the question, are these adipocytes the same in the bone marrow from a high-fat diet individual as it is from calorie restriction? So Miriam Bradella did bone marrow aspirates on these volunteers that got paid $7,000. And we got a look at what was going on. So initially, no surprise, circulating IGF-1 goes down, also goes down locally. So that had one impact. But we were more interested in an unbiased approach. So we looked at, and this has just been out in the last few months in Frontiers, high-calorie diet versus fasting. So they're the same adipocytes microscopically. They're the same stromal cells, and we grow them out in culture. But they're very different. Their genetic transcriptional profile is very, very different. There's only 3 genes that overlap between the 2 patterns. And when we look at the gene ontology separation, it's very interesting. Obviously, metabolic processes is a big deal. Bottom line, and I didn't include, but it's in the paper, is that calorie restriction is associated with an inflammatory response. High-calorie diet is associated with actually suppression in inflammation. And that paper is at Bone Research and hopefully will be accepted soon. But PD-1 and PD-L1 are markedly increased in the high-fat diet animals. T cells are expressing PD-1 and PD-L1, and it's suppressing marrow inflammation. On the other hand, in calorie restriction, you have this different picture, and it's inflammatory, even in humans, and its complement factor D is one of the big human genes in adipocytes that's upregulated, and one of the top genes, as well as IGF-1 down below with calorie restriction. You can see the difference in the patterns of genetic transcription. So, bottom line is that marrow adiposity is associated with this increase in complement factor D, adipsin. Knocking it out prevents it, most of the marrow adiposity, and does restore the skeleton. And we're currently working on an even more adipocyte-specific, bone marrow adipocyte-specific conditional deletion. So what do we have? We know that the skeleton with 30% calorie restriction, humans and mice, increased bone marrow fat. That marrow fat may be, as Gustavo said, may have a negative impact on the skeleton, but may also have an energy source. So depending on the metabolic status of the given animal, it may allow for lipolysis and release of fatty acids that are needed by the osteoblast, or it may have a negative impact like adipsin has in terms of suppressing osteogenesis. You see this decrease in IGF-1 and IRS signaling that occurs. It impacts the cortical skeleton. You get this trabeculorization, which we think may be related to an attempt to suppress bone resorption, but that still needs to be decided. So the bottom line, what is the skeletal response to weight loss? Is it physiologic or pathologic? And the answer is probably it's both. That there probably is some compensatory mechanism that's inherent when we lose weight that allows the skeleton to adapt. We know there is adaptation that occurs with aging in the periosteum. So But it also causes bone loss, and the skeleton's not happy about having bone loss, both at loaded and non-loaded sites. So it's probably not all gravitarily related. And almost certainly, I think, relates to metabolic shifts that are occurring at the cellular level that are changing the characteristics of both the periosteum and the trabecular bone. So can we mitigate, and this is for Wendy, can we mitigate bone loss at all? And both Wendy and I share a common mentor, Dave Clemens, who published nearly 50 years ago this beautiful study in which he fasted individuals and showed that IGF-1 was reduced, and that if you gave protein, not calories, but if you gave protein, you could restore the serum IGF-1. And so with that model in mind, we proposed and have started the GRAMS trial. So GRAMS is an abbreviation for GLP-1 receptor agonist musculoskeletal preservation. Got to have a good name, so this is a good one. So these individuals are going to be treated. They just started randomization with tirzepatide, and they're being used as their own control, high protein supplementation with Ensure, and then some physical activity to see if we can mitigate the GLP-1 effects on bone, and looking at both MRI and muscle. So we are going to look at muscle as well as bone. So what are our challenges? I still think it's very difficult in our world, in our scientific world, to understand when we use mice particularly, how much of the mouse effect is a compensatory effect and how much is pathologic. And trying to sort that out, I think in this case is really important. How does the brain sense what's going on in terms of calorie restriction to impact bone? Is the central signal from the brain telling bone progenitors to become adipocytes for storage? Because at the end of the day, in starvation in humans and in mice, the marrow is full with fat cells. So there's got to be some mechanism that drives that. Is it all at the cellular level, or is there a central mechanism? And then how does, and this comes back to Gustavo's talk, how does the marrow communicate with brain and within itself to mediate these effects? And are these truly compensatory effects, or is that pathologic? And finally, and I think this is the most important thing, is we're in this business to do clinical studies because we want to know what happens in humans. And the inability or the reluctance of industry to allow us to use these agents in large clinical trials is really a limiting factor. We need to understand what happens in the skeleton and in muscle in individuals who are GLP-1 agonists. And we have more and more coming out. So these are not going away. There's just going to be more and more people that are going to use them. There's a paper from the group at Pennington that has shown that bimagrumab, which is an activin antagonist, so it's blocking myostatin, which Gustavo talked about. If you add that to semaglutide, you can protect some of the skeletal effects, but then you have some side effects from the activin inhibitors. So trying to get into that perfect Goldilocks situation where you have something that can protect the skeleton and not be have negative impacts at the same time that you're using the GLP-1 agonists is going to become a real challenge for our community. So with that, I think I'll stop, and this is our lab group and lots and lots of collaborators around the country. But thanks for your time, and happy to answer questions. Yeah, great question. Yeah. So growth hormone goes up with calorie restriction, no question about it. And that's the major driver. But at the liver level, there's hepatic resistance to that growth hormone. For some reason, the liver cells that make IGF-1 are resistant to growth hormone. So yes, growth hormone does go up with calorie restriction, goes up in mice and in humans both. But it's that peripheral resistance to induction of IGF-1 that is a feature of everything we see with fasting and calorie restriction. Mechanism, not no. Great question. Yeah.
Great talk.
Thanks.
So coming back to the semaglutide, so is it the muscle loss that's causing the bone loss? And,
Great question. So that's a great question. That's why Gustavo's talk was so good, because that's it. So we're working on that. So we have, this is a great little drug. So we have a monoclonal antibody which is tagged to IGF-1. And it has a affinity binding for muscle. And we just started testing that for its skeletal effect. So it only goes to muscle, it doesn't go to bone. But with calorie restriction, we are trying to figure out if that impact is really at the muscle-bone interface. So it's a cool little, Cavalry's the company that we're working with. But it's a cool little agent because of its impact on muscle. And they've had great studies in muscle that show that this compound actually does build muscle mass and is useful in some anabolic states in preclinical trials. But they never looked at bone, which, we go back to this irony that they're two separate worlds and they don't interface. So we're looking at it in bone and we'll see what happens. But it's a great question and we'll figure it out, maybe.
First of all, I'm just going to say thank you for an excellent lecture. No big surprise with how good it is, and thanks for all that information. I'm going to ask one quick question before I pass it on, and that is just, I'm not convinced that there's greater amount of muscle and bone loss with semaglutide or GLP-1s because they're losing so much weight. So if you just comment on that and having control for body weight,
Yeah,
I don't think it's more than the
yeah, so that's a good question. I mean, they're obviously losing 15-20% of their weight. But even, at least in our studies, when you adjust for body weight in the male mice, they're losing muscle mass. So that is a component of it. And, the bimagrumab study really does provide some indirect evidence that is protecting muscle mass at the time that these individuals are losing weight. So that paper didn't make it at New England Journal, Chris. I mean, it's a great paper, but statistically it wasn't good. And so it's out somewhere else. But that's an important paper because that's where industry is going. They're going with all these new designer activin inhibitors, et cetera, that can protect cortical bone and lean bone. So those studies are going. I think we can do it with just protein, but we'll see.
I'm just going to say one thing for
Yeah.
lifestyle. They were obsessed with lifestyle with the bariatric patients. They didn't even think about it for all those patients. But when you say mice, that it happened in
Yeah.
mice, then I'm convinced it's
Yeah.
not just because lifestyle was ignored.
Yeah, it's a good question.
Clinically, with rapid weight loss and the
Yes.
growth hormone resistance
Yes.
that happens, we also see a rise in cortisol.
Yeah, great
What is
question.
the role of glucocorticoids in
Yeah.
this?
Yeah, so that's a great question. And Gustavo and I had this conversation with Marcus Seibel, his colleague in Australia. So we looked at that, and we have a paper at JBMR where we knocked out beta-hydroxysteroid, which is the hydroxycortisol, which converts cortisol to cortisol, and then did calorie restriction. And we were able to get some protection in the skeleton. So at least there is some evidence, and we see it in anorexics. I mean, we have another paper that shows that cortisols go up in anorexia, and that it's an important component of the hormonal changes that occur. It's not a complete rescue, and we're not sure we understand all the mechanisms. There's also a sexual dimorphism, which may make females more prone to worse bone loss with calorie restriction. So, but yes, cortisols, and we actually did cortisol measurements in the marrow from the human biopsies. and they also showed an increase within the marrow space of cortisol. And you could say, oh, well, it's up in the circulation, but we showed that the marrow serum is very different proteomically from what's happening in humans. So you have this picture of the marrow as a very enclosed space that's very protective of their own cells. And so they are doing things independently of what's happening in the circulation. And it's really an interesting story because, as we all know, and Christoph probably knows better than any of us, that with obesity you get increased macrophage infiltration in fat cells and you get this whole inflammatory process. That's the whole story behind obesity, is pro-inflammatory. When you look at the marrow, it's exactly the opposite. These PD-L1 and PD-1 ligands are actually suppressing inflammation, and whether that's a means to allow peripheral fat cells to get to these, peripheral macrophages to get to these fat cells is unclear. But yeah, it's a whole different space, and so the models are not good. So the in vivo models are really something we struggle with. Now, how do you really compartmentalize the marrow space to get at the questions about what adipocytes can do negatively or positively to the skeleton? Very, very, there are no good in vivo models, ex vivo models. Hi, Judith.
Hi, Cliff. So I have a non-bone related question.
Okay.
Sorry. But actually it is. It's fascinating that you get this completely opposite effect, that your RNA-seq data.
Yeah.
In
Unbelievable.
I mean, that was just really shocking to me.
Yeah.
What is the time course of development? Like you, both of your interventions are long-term, right? The high-fat diet and the calorie restriction. So are they, are these opposing, transcriptomes happening quickly?
Yeah.
Is there any diurnal variation in?
Yeah. So Judy, you know, I wish you were still in our lab, because we actually just got IACUC approval to do a 16-hour fast in mice and ask that very question. Is this effect very acute? And if it is, does it modulate over time? So for example, if we go back to humans, in very severe anorexics of long duration that have had bone biopsies, and there are many of them, but their marrow now is very gelatinous. It's not, the marrow fat has gone away, and it's become very gelatinous. And so I think your point is very well taken. There's an acute. I think what we're dealing with here is subacute. The changes are subacute, and then we have what happens chronically, long term. And so same with some of the Holocaust survivors, that they looked at their bone marrow from those individuals and those in Amsterdam during the very severe starvation that occurred in 1945, and it was all gelatinous marrow. It had all gone to, the marrow adipocytes had gone away, and you could argue that maybe they used up all their lipid, fatty acids for energy. But I don't think there's any question, at least we feel, that some of that marrow fat, at least with calorie restriction, is a compensatory protective mechanism for the skeleton. What happens in high-fat diet is totally different. The proteomics are totally different. And so just like the gene transcription, the proteomics in that paper, you might look at it, the Frontiers paper. That was Sam Costa, who you might remember, was our graduate student when you were in our lab for too brief a period of time.
That was a very interesting talk. Thank you. I learned a lot. My question is about the adaptive immunity status. So if the bone marrow adiposity increases, and you talk about the complement situation, but what happens to the lymphoid lineages in the bone marrow, and how would that translate to the adaptive immunity status in the calorie restriction?
Yeah, great question. So the Tregs are increased dramatically with high-fat diet. So there's an attempt to really tamp down the immune response in the marrow. It's all Tregs. In calorie restriction, we haven't done enough to actually look at how the immune system is altered, except to say that we get this inflammatory profile that's consistent, not inflammatory cytokines, but an inflammatory type lymphoid population, which looks like it's trying to respond to a signal of injury. And I think we try to get as simplistic as we can to come back to think about how a mouse could do all this stuff. But calorie restriction is a real injury model. When we think about marrow fat, it's injury. So it's not just calorie restriction, it's not just high-fat diet, it's radiation, which reproducibly induces marrow fat. Within 3 days, you see marrow adipocytes. And Christie's former boss, Phil Scherer at UT Southwestern, is doing a study with us to look at whether those adipocytes are new adipocytes that are being recruited, or they are adipocytes that have been latent and are now filling up with fat storage. So we can answer that question. But so I think the bottom line is we still need a better understanding of what's going on. But when we look at the cytokine profile in the calorie-restricted mice, they do have some of the pro-inflammatory IL-6, TNF things that were surprisingly are present in the marrow serum. So that's kind of shocking, because we do calorie restriction to help us do better in life. So it has some real implications for what we can do therapeutically.
Any other questions? Dr. Breslin.
Hi, thank you very much for your talk. This may be a naive question, but inflammation is healing.
Right.
And it's part of tissue remodeling.
Right.
When you get a cut in your skin, you have to regrow your skin there. And
Right.
inflammation is part of the process. So since bones are remodeling with weight loss, maybe inflammation is helping remodel.
Yeah, no, that's a great question, and trying to understand the characteristics of the macrophages that are important in that process is something we thought about, that maybe the anti-inflammatory nature of that healing process could be that those types of M2 macrophages are the ones that are really involved. We just haven't been able to characterize them well, but that's a great point. And we always wondered why bone remodeling doesn't trigger a huge inflammatory response, and you have breakdown of the skeleton. I mean, you have the release of all these enzymes, and all this calcium goes out. So it is a normal inflammatory response, I guess. So.
Another naive follow-up question is, as people lose weight, particularly a lot of weight,
Yeah.
if they wear compensatory weight vests to
Yeah,
maintain weight,
yeah.
does that maintain anything?
Yeah, okay, so that's a great question. And the study's been done by Kristen Beavers, where she looked at loaded weighted vests for the skeleton, particularly for the trabecular bone in the spine. No effect of weighting on skeletal loss. So a big negative. Just recently published, you'll find it somewhere in the literature, but nice study, randomized controlled trial with weighted vests, calorie restriction, older individuals who were obese. So one of the questions that always comes up is, what's the difference between obese individuals that undergo calorie restriction and healthy individuals? Because the calorie study was actually healthy individuals, mid-30s, very healthy. They lost bone. There's obesity somehow protect. Carolyn's data would suggest it doesn't. So I should just point out that one of the other, we get also funded, Carolyn gets funded by NASA. And so one of the important elements is trying to understand how the skeleton adapts or maladapts to different programs. And the GLP-1s are starting to be used extensively in implanting of knees and hips for obese individuals who are more prone to osteoarthritis. These individuals now preoperatively are getting GLP-1s for 4 to 6 weeks in advance or longer to lose weight. They have better skeletal outcomes as their obesity gets better. Skeletal outcomes being what Stryker wants them to be, that is that their implant doesn't fail, but whether it has the skeletal bone loss component is another story. So,
Really interesting stuff, and indeed, most of the people who lose that 10% weight loss with moderate weight loss, a little bit of extra weight didn't do anything. The best study, and
right, yes.
it makes sense.
Yeah, it does make sense. It's a non-gravitary, you think? So this is pathologic, do you think, Sue?
I think it's pathologic, metabolic,
Yeah.
related, and nothing to do with the weight.
Yeah, good, good. That's good.
All right, thanks so much. Such a great talk, two talks, and we
Well, thank you for all for attending. We will have lunch and then focus session. But before I conclude this part, I want to do say some note of thanks. This annual Pioneers in Endocrinology Workshop is sponsored by the following partners: the Rutgers Endocrine Program, Department of Animal Sciences, Robert Wood Johnson Medical School, Division of Endocrinology, Metabolism and Nutrition, the Next Center, New Jersey Institute of Food, Health and Nutrition, Research Diet, Ascendance Pharma, and special thanks for compiling this year's abstract booklet and coordinating the day events goes to the following individual: Kista Skagner, Stacy Pontario, Nick Bello, Aaron De La Rosa, Glenn Barger, Omkaram Gangesti, and many other students and undergraduate students. Thank you for joining. Please go ahead and have lunch in the other side of this podium.